Now we're going to start with integration, which is also known sometimes as antiderivatives. Notice here I have the time and velocity. Those are my two axes. And we also know that distance is equal to rate times time. Consider an object moving at a constant rate of 3 feet per second. There's my 3 feet per second. And I'm going for 4 seconds. If we draw a graph of the velocity, since it's a constant, it would just be this. This is the graph of v equals 3. And then if I go for 4 seconds, that's the end. And if I multiply velocity, which is rate, times time, velocity times time, I should get, and I do get, distance. Here I can notice that I get 12 feet. If I go 3 feet per second for 4 seconds, I've gone 12 feet. And also, it's the same as this area, which would be 4 times 3. So we can see that the area has something to do with distance and rates and times. And let's see what we can figure out. Since we don't have a way to take the area under something that's curved, what we're going to do is we're going to do some estimating. I'm going to estimate here. I'm going to make 2 boxes, 2 rectangles, and I'm going to estimate the area of each one of those rectangles. I'm going to add them together, and I will get some value. We have a few different rules for how we make our rectangles. We have the right-hand rule, we have the left-hand rule, and we have the midpoint rule. And this one is actually using the midpoint. We can see if we used the right-hand rule, then I would start at 4 because I have t equals 8, and I'm making 2 boxes, so each one has a width of 4. If I use the right-hand rule, here, if I would start here at 4, and I would make a rectangle like that, and then 8 would be actually up here on the graph, and that would be my rectangle for 8. So you can see if I use the right-hand rule for this, I would have a lot of overage. Here, I'll say if I use the left-hand rule, then I would be starting at 0 because that's the left side. And if I made a rectangle, I would actually have no area for the beginning rectangle. And then the next one for left would be here. I would have a rectangle that looks like this. And we can see that this would be over and this would be under as far as the area goes, because the green, I'm missing a lot of area, and the yellow, I have a lot of extra area. The midpoint is actually one of the better estimates, because this much right here is all over on top of the curve, but we're missing this much, right? So no, they're not exact, but it's a little better. We can kind of say, they fill it in. And this part right here, which is not under the curve, makes up for all this that is missing from the area under the curve, right? So the midpoint rule is usually the better or the more accurate. So anyway, if I make 2 rectangles, it looks like this. Now, if I make 4 rectangles, it's getting a little better. I mean, this is a closer estimate of my average. And if I made 8 rectangles, it's even better. It's even a closer representation of the area under the curve. And if I make 64, now notice how close this is. There's a little bit above, like if I think it's clear that this is the better estimate. Okay, so what would be the best estimate? The bigger n gets, or the more rectangles I'm putting in between here, the closer it gets to the actual area under the curve. And that's really what integration is. So so consider we have this region R bounded by the graph of a continuous function f, and the axis and the x-axis between x equals a and x equals b. I actually have a picture on the next page. Here, I'll just draw this in while I'm writing it. So let's say I have, here's a, here's b, okay? So consider the region R bounded by the graph of a continuous functions f between a and b. So it says the net area, not the total area, the net area, this is very important here, of R is the sum of the areas of the parts of the graph that lie above the x-axis. So this side here and this side here, we add those areas. They lie above the x-axis. And if I want to find the net area, I subtract the sum of the area that lies below the x-axis. So that would give me my net area. It wouldn't give me my total area. My total area would be if I added each one of these. And we do that sometimes, depends on what we're looking for. But if I'm looking for my net area, this is what we're getting. All right, so here is probably a better picture of exactly what we're saying. So here's A. Here's our A, and here's our B. And everything in this greenish color is above the x-axis, and everything in the pinkish color is below the x-axis. And here, what this says is we're dividing it up into 6 triangles. 1, 2, 3, 4, 5, 6, right? Here, this says I'm doing the exact same thing, only now I'm using 4 rectangles. If I said triangles, I apologize, I meant rectangles. But it doesn't matter. It's still the same. I can explain this summation F. Let me explain it. Since we are looking at the midpoint, this is actually a midpoint rule. I can see because there's my midpoint of the graph, and I've created that rectangle, excuse me, with that height. So if I want to know the height of this, if I want to know the area of that first rectangle, well, it's the base, right, times the height. That would be the area. How wide is that? We don't know, because we don't know what A and B are. But delta X, we can say is equal to B minus A over N. Here, N is 6. Between 1 and 7, then delta X would be B minus A over 6, which equals 1. So that means each one of these has a width of 1. Okay, so that should be clear. And then the height is always going to be whatever my f of x is, which is my y. But notice there's different x's. So that's why we call it x sub, maybe we can call it x sub n. So that way, when we sum these, we can go from k equals 1 to 6. We can still use 6. And we would say this is f of x sub k times delta x. So this right here is adding all the areas of each one of these rectangles. And that's basically what we're doing, okay? The more rectangles, the closer we get to the actual value. Here we have 75 intervals, and here, notice, n is infinite. And as you can see, basically it's colored in. When n goes to infinity, we're basically, I can't do it, I'm sure, but sorry. Basically, we're just taking a line, and then we're gonna put another line like right next to it. And then we're gonna put another line right next to it. And as you do that, and a line really has no width, it means n goes to infinity and delta x becomes closer and closer to 0. Notice how when n goes to infinity, we have the actual area of the curve. So for this problem, if we want to know what the net area is, the first thing we always have to do is, if I was given this equation, y equals 2x minus 6, I would have to find where my 0 is. I would set this equal to 0, and I'd get x equals 3. And that's my 0. Let's say I go from 1 to 6 here. I would check and I would say, okay, well, what happens when x equals 2? When x equals 2, I get a negative value here, right? I don't really care if it's positive or negative. I don't care what the number is right now. All I'm saying is it's below the x-axis between 1 and 3. And if I plug in 4, I get a positive, which means it's above the axis from 3 on. So that really helped me if I didn't have a picture. I can now easily draw this picture and easily figure out my areas. The area of this is 4. They're both triangles. And the area of this is 9, 1/2 base times height. And I would say that my net area is equal to 9 minus 4, which equals 5. That's my net area. If I was asked for my total area, it would be 9 plus 4, or 13. But my net area, which is what you get when you integrate, is you get net. If you remember back to when I was doing the sums, the last sum I did, if I add everything up, all my areas up, or all my pieces up from somewhere to somewhere, and then I go from that next place to the end, that's really the same as what this picture right here is showing us. This right here means integral or antiderivative. If I want to know what the area under this curve is between A and B, I can say, well, let me add from A to C. Let me find what that is, and I can add it to this, and I would get the same as my original.